Hello everyone, this particular chapter is on oscillations, a bit of a new thing for us to talk about. So first of all, we're going to be discussing in general what's known as periodic motion. You can think of this as just any type of motion that repeats itself over and over and over and over and over again. It could be something like a heartbeat like we see over to the right there. Maybe it's a clock ticking, maybe it's a kid on a swing, maybe it's people hitting a tennis ball back and forth. It's just some type of motion that has a certain amount of time that it takes for it to repeat, periodic motion. So we've got some definitions that we're going to be using over and over again. So first of all, a cycle is one repetition of the motion. One over and back, one time around, however you want to think about that. A period is the amount of time for one cycle. And we're going to use capital T to represent period, and it's going to be measured in seconds. Keep in mind that the cycle itself is sort of dimensionless. We could a little bit more technically represent this as the number of seconds that's required for each cycle, but because the cycle is dimensionless, we leave that off. Just say it's a number of seconds. Let's see, number 3, the frequency. The frequency, we'll use a lowercase f to represent that, and this is the number of cycles each second. The number of cycles each second. So you could think of that as cycles per second, but then again, cycles are dimensionless, so this is just 1 over seconds. And by definition, 1 over seconds is equal to hertz, Hz. So our units of frequency are going to be hertz as long as we're measuring how many cycles happen each second. You could think of frequency as measuring sort of how rapid the oscillations are. Does it just go over and back one time in a second? Or is it a bunch of times in each second? How rapid are the oscillations? The period and the frequency clearly have a relationship between them. We could say that the period is equal to the reciprocal of the frequency, or vice versa. Either way would work just fine. There are a couple of more that I'd like to add to this. Let's see, let's put a number 4 here at the bottom, which is the angular frequency. And some of what we do with angular frequency is going to look really familiar, and there is a connection that we'll see a little bit later in this lecture. For this, we use the symbol omega, which we used for angular velocity before. It is equal to 2 pi times the frequency, which according to the relationship between the frequency and the period is going to be 2 pi over the period. So keep this one in mind. A little bit later in the lecture, we're going to connect that back to angular velocity. And then a number 5 is the amplitude. The amplitude, which we have A for. And you can think of this as just the maximum displacement from equilibrium. The maximum displacement from equilibrium. So these are some basic definitions that are going to apply to all types of periodic motion, but we are going to, well, here's just some examples. You can look through that to get some ideas of different periods and frequencies, but nothing to really talk about there. We're going to focus on one specific type of periodic motion, which is known as simple harmonic motion. So this is a subset of periodic motion. So this is a system that oscillates, but now it has a very particular way that it oscillates and is periodic. It has a restoring force, and we've had an example of a restoring force before. You can think of this just in general as a force that points back to equilibrium. Just like we had with the spring, and you can see just below the example that we're going to use as the spring and mass system. So we have a restoring force that when we look at the equation for the restoring force is directly proportional to the displacement away from equilibrium. So the perfect idea of this is the mass and spring system, which of course might look something like this. If we looked at it horizontally, we have a spring it's attached to a mass, and perhaps at this location is x equals 0, and then we could stretch this way or compress this way. And the force is always going to be trying to get back to equilibrium. So if I'm over on the stretch side, the force that's coming from the spring points this way, and if I'm over on the compression side, the force is going to point back that way. So it's just like what we learned before, and we talked about this a bit before. We know that the spring force is equal to negative kx, but we often just look at the magnitude of this, which is just kx, and you'll notice, there we go, we have a displacement, and it's directly proportional to the displacement according to the spring constant. This is a good example for simple harmonic motion that works for small displacements. And if we were to just look at experiments and see if it matches the equations that we have for simple harmonic motion coming up, you'll find that it diverges a little bit as we get to larger and larger displacements. So as long as the displacements are relatively small, this works out just fine. So let me add here at the bottom one additional thing that we're going to need a little bit later. If the only force that I have acting in this situation in the x direction is the spring force, so we can say that Fx is, let's write it this way, is the spring force is equal to negative k times x. And as long as that's the only force, we can also say that that's equal to mass times acceleration in the x direction. If only force in the x direction. So we can go from here and solve for a couple of different things. Actually, just one thing. Let me take this part of the equation and solve that for the acceleration. We'll see that the acceleration is minus k over m times the displacement x. Minus k over m times the displacement x. And I want you to keep that equation. We're going to use it on a later slide. Not yet. You'll see what it's for in just a little bit. So, a couple of questions here. First of all, mass on a spring in simple harmonic motion has amplitude A and period capital T. What is the total distance traveled by the mass after a time interval t? Well, for a time interval t, it has to go through a complete oscillation. So let's just say, for instance, that we stretch it over this direction. And we start here. And at this point, this is going to be the maximum positive displacement, so that's amplitude A. And then it's got to get all the way back to that point to be one complete oscillation. So you can imagine starting here, it's going to go an A in this direction, and then it's going to go over here, a distance A, and then back to the middle, and then all the way back to here. So our answer here is 4 times the amplitude in order to go through one complete cycle. And for whatever reason, I left the answer slides into this lecture, which I haven't done all semester. So there you go, 4 times A. If, on the other hand, we wanted to look at the net displacement, well, of course, we're looking at the starting and ending point in that particular case. So we're back to where we started, so the displacement is 0. And there's the answer slide for that. So we're not going to do this one. We don't need that slide. Instead, we want to develop a little bit of the mathematics that's related to this. So again, let's look at the mass spring system. And all we're going to do is we're going to take the mass, we're going to maybe start it here in the middle, and then pull the mass over this direction and let it go. And the way we're doing it here, let me erase that, I went too far. Notice they're looking at just the left-hand side of the mass where the spring is connected, and we're going to pull it over here and let it go, and then it's going to oscillate between positive A in one direction and negative A in the other. So it's going to go back and forth like that, okay? Now, to keep track of that motion, we're going to imagine that perhaps we could take some paper underneath. Notice it says a strip of paper, and we've got an apparatus that just pulls the paper this way at a constant velocity. And then they've attached a pin right to this edge of the mass at the end of the spring, and it's going to draw on the paper as the mass oscillates back and forth sideways between A and negative A. So if that happens, you can imagine that it's literally just drawing exactly where it's located at every point in time. So the way that they've drawn this line for starters, you can imagine that the mass is at this location and it's moving this particular direction. And you can see that, well, it drew a line that kind of went like this. And then as the mass goes back to the right, it draws a line that goes to there. As the mass goes to the right further, it goes to there. And it's basically for every point in time, and yes, time is on this axis, it's drawing the location of the mass at that every individual point in time. Now, if we take that graph, that piece of paper, and you can see kind of physically how this is being drawn by the motion of the mass, and just look at the graph. Let's flip it sideways. We can see that on the next slide. And again, this is being drawn by a mass that's going back and forth like this, being pulled by a spring. And as that happens, this is tracking the location at every individual time. So we have a position versus time graph. And you can see that we get a curve that's essentially sinusoidal. Depending on where we decide to start the curve, it could be a sine or a cosine curve either way. In this case, we're starting at t equals 0 at the maximum amplitude. So this is a cosine curve. So you can see as the mass goes the maximum amount in either the positive or the negative direction, that represents the amplitude. So that's the positive amount, amplitude in the positive direction. This is amplitude in the negative direction. It's the maximum that it ever gets from displacement. At this point, it's as far as it's going to go in the positive x direction, and the next time it gets there is at this point. So you can see from here to here, we've essentially got one cycle. And we could pick any two corresponding points, whether that be here and here. That would represent one cycle. As long as it's at the same point and traveling in the same direction, we have one cycle. So since my horizontal axis is time, well, that one cycle corresponds to one period, the amount of time it takes for it to repeat itself, to go through one exact cycle. So we can mathematically represent the curve that you see there with an equation that looks like this. X as a function of time, the location, the position of the end of the spring as a function of time is equal to the amplitude times the cosine of 2 pi over t times the time. So I can plug in different values for time, and it's going to tell me exactly where the mass is. You may recognize from an earlier slide that this is the same thing as a cosine omega t. No difference there at all. So if in this particular equation I plug in t equals 0, so let's do that. Let's see. At t equals 0, what are we going to get? Well, the cosine, in that particular case, the cosine of 0 is just going to be 1. So I'm going to get that x is equal to a, which makes sense. Here's t equals 0. Notice the location at that point is a. So everything works out perfectly there. So if I were to plug in, let's see, t equal to 1 period. So in other words, we've waited a period t, we've gone through one cycle. We should be right back where we began. Well, if you go back and look at the equation here above, if I plug in t there, capital T, the t's are going to cancel, and I just have the cosine of 2 pi. I've gone all the way through one loop. Cosine of 2 pi is going to give me the exact same thing. I'm going to get x equals a. So you can see that this fits the curve that we have below. Let me make one point, and that is inside of this needs to be in radians. So whatever numbers you plug in there when you evaluate the cosine function, make sure you're using radians for this to work out. Okay? Now, Something I referred to earlier, simple harmonic motion, it turns out, is connected very tightly to what we learned about uniform circular motion. And we can look at this example. We're not going to derive these equations. I want to give you some stuff, but just kind of physically show you how these things are connected. And then we'll be basically done with this first part of the lecture. So let's imagine a couple of different things here. First of all, at the top, we've got what we had before. We've got a mass connected to a spring, and it's oscillating back and forth in this direction. So you can imagine it slows down as it goes this way, it stops, and then speeds up, speeds up, speeds up. It's going fast, it slows down, slows down, slows down, stops, speeds up, speeds up, speeds up, speeds up, speeds up, goes down, slows down, stops, and it's kind of going through that type of motion. It's always changing velocities between 0 and some maximum velocity. So if you imagine in front of that, I have a turntable that's rotating around this way, and what we're doing is just, they've got this little vertical peg that's connected and some light shining this direction, such that the shadow of that peg at every point is being shown on a screen that's just below the mass. And then imagine that peg rotating around this direction, and you would see, well, this shadow move this way. When it's here, it's going to be right there in the middle. And as it rotates further around this way, well, the shadow is going to go there. And then as it rotates around the front side, of course, the shadow is just going to go back the opposite direction. So as this turntable rotates like this, you get the exact same motion of the shadow of the peg. So we could say that the shadow of the peg matches the mass location. As the peg itself moves in uniform circular motion. And of course, well, it doesn't necessarily match unless this thing is rotating at just the right angular velocity. If it's going too fast, well, then the peg shadow is going to go back and forth too quickly to not match the spring. But you might be able to imagine a situation where if I get the turntable rotating at just the right velocity, just the right angular velocity, well, then as the peg moves around in that uniform circle, the shadow of the peg has motion that matches the back and forth motion of the mass. So let's see if I can get this at a certain angular velocity. Again, that's the angular velocity of the peg. Needs to correspond to omega, the angular frequency of the mass, or of the peg's shadow. It turns out they're the same. We're using two different names here for exactly the same quantity because I can think of this two different ways. Even as the mass is just moving linearly back and forth, I can kind of imagine one repetition as being one trip around the circle, and I get the exact same results. All the math is identical. So there is a long derivation that we could go through to sort of get some equations that work for both of these problems, but I want to present you with some of those equations and not go through that detail. So first of all, just don't have the time for it. So first of all, we know that this is true. We know that x is equal to a cosine of omega t. X is equal to a cosine of omega t. From that, if you wanted to do a little bit of calculus and instead of working through this derivation, you could find that the velocity, and again, this is the velocity of the mass moving back and forth, is equal to negative a omega sine of omega t. And it turns out that you could look at this particular equation and deduce that the maximum velocity is going to occur when we have the sine function equal to 1. And if I'm just looking at the magnitude of the maximum velocity, it's going to be equal to a times omega. And then we can go one more time, and if you were to take another derivative, which you don't necessarily have to do in this class, we could find the acceleration as a function of time, and you would see that that's equal to negative a omega squared times the cosine of omega t, from which you would find that the maximum acceleration is equal to, at least the magnitude thereof, is equal to a omega squared. Again, that's when the cosine function goes to 1. That's when that's going to be a maximum value. So don't forget this, let's use a different color. This position, this velocity, and this acceleration are the position, velocity, and acceleration of this mass as a function of time. So these three equations tell me exactly what's happening at every point in time for the spring mass system as it moves back and forth. And we can look at a graph of these and kind of see how they relate. So first of all, our position versus time graph, which is exactly what we saw a few slides ago. We see it as a cosine function. It starts at the amplitude, the maximum amplitude, and goes back and forth, as you see according to this blue curve. However, keep in mind, when it's at a maximum amplitude, when it's all the way at the end, that's when it's turning around. It has to stop to turn around. So that corresponds to a velocity of 0. And you see that every single time I'm at the maximum position, the velocity is 0. Maximum position, velocity is 0. So that agrees. When it is displaced in the positive x direction, positive x, remember it wants to get back to equilibrium. It has to go into the negative direction to do that. And you can see down here we have negative velocities to make that happen. Once it is all the way back to equilibrium, that's the point where it's moving the absolute fastest. And you can see that track through all the way over to here. Again, now we're going in the positive direction, and we have a maximum velocity that corresponds there that's in the positive direction. And then that velocity is going to decrease, it's going to slow down until we get to 0 when it's turning around in the positive direction once again. So think about the motion that's happening at all points between positive and negative amplitude, and you should see that this velocity graph matches what you'd expect. And also, it simply is a graph of that particular equation. We could do a similar thing with the acceleration. And these graphs are all supposed to line up so that you can compare it above to the velocity as well. Let's see. So first of all, this acceleration graph is a plot of that equation. So here we're starting at maximum amplitude in the positive direction. That's when the acceleration is a maximum in the negative direction because the force is pointing in the negative direction at that point. When we are in the middle, when it's moving the fastest, well, that's the point where it's not stretched or compressed. That's where the force is equal to 0, so there is no acceleration. And you can continue to track this through, and it should make some sense. When I'm in the maximum negative direction, that's when the acceleration is at a maximum in the positive direction, and so forth. Notice how all of these things line up and correspond to each other. Here we can draw another comparison between these 3 points. Here I have maximum positive acceleration, so positive A max, corresponds to negative amplitude, corresponds to velocity equal to 0 because it's at the point where it's turning around. And you should be able to correspond these 3 points together at any point on the curve and see that they make some sense, ideally. Okay? So from before, let's see, we had an equation that looked like this. We said that the acceleration is equal to negative k over m times x. Okay, negative k over m times x. Well, now we have a new equation that you can see just above here. And let's just compare their maxima if you want to. So let's see. So in this particular case, we're going to use this value. So we can say that this is also equal to negative A omega squared. So let's see. Actually, let's not write it that way. Let me back that up just a little bit. Let's say we're not using the maximum value. So here we're not going to have a value of just A for the amplitude. Instead, that's just going to be X, because it could be any position, not the maximum, times omega squared. So just comparing those two equations, that means that this is equal to that. So negative K over M is equal to negative omega squared. So the negatives cancel each other out, and we can say that omega is also equal to the square root of K over M, in addition to being equal to 2 pi times the frequency. So all of these things are connected a little bit. So let's see, we can deduce a couple of other equations from that, and I'm very much out of space here, so let me move a couple of things over. Let's see if we can get that over to here. It's not exactly what I wanted, but you get the idea. We can take this equation and rearrange it, and you'll see that the frequency is equal to, let's see, 1 over 2 pi times the square root of K over M. Or we can take the reciprocal of that, and you'd see that the period is equal to 2 pi times the square root of M over K. So a couple of other equations that are going to come in handy. All right. So let's see, a few different things. Mass on a spring, mass system in simple harmonic motion, amplitude A, period T. Is there a point in the motion where V is equal to 0 and A is equal to 0 at the same time? Well, no. That's not ever going to happen, because they happen at two different points. V is equal to 0 at these endpoints. A is only equal to 0 in the middle, so those are not going to correspond to each other, right? Let's see. I'm going to stop the recording now and do this one in 2 parts, so that's the end of part 1. Make sure you click the link for part 2 as well.